Hello, my chemistry friends, and welcome to today's lesson. We're continuing Unit 7. Hopefully you have already finished your warm-up. Today we are doing Lesson 7.3, where we'll be talking all about catalysts. Your classwork today will be a lab. It's one that a bunch of you have been asking about since the beginning of the year. Sad but true, we don't get to do it in person, but I am recording a bunch of videos for you all. I'll be doing the reaction live in office hours later this week on Friday. And then as soon as we're back at school, I promise I will invite all of you to come and we'll do the reaction in person. But for now, let's go ahead and get started. Here are your learning targets for today. The first is I can accurately predict the effect of changing various factors on the rate of a chemical reaction. We've already done some of this with our most previous lab where we looked at how temperature changes how fast or how slow a reaction will happen. And so we're going to look at the rest of those today, and the last one being a catalyst. And so we want to explain how a catalyst is able to speed up a chemical reaction. So here's your to-do list. Hopefully you've already finished your warm-up. You are currently doing either the live lesson or the Edpuzzle. Your classwork today, which will be due next week, will be lab number 16, and then you will end with your exit ticket. So as a reminder, the focus of Unit 7 is how fast or how slow reactions happen, and it all boils down to collision theory. So this is the last time this slide will be in here, I promise, but I do just want to reinforce this, that in order for a chemical reaction to occur, as you can see here in this little video, for A, B, and C to come together to make their new product, the particles must collide. And the particles collide, they must be an effective collision, which means they must collide with enough energy and in the correct orientation or position. Okay, so that's the last time you'll see this slide, but it's extremely important and it's going to be kind of the focus of the first part of our lesson today. So this is our potential energy diagram, which we looked at in our last class. As you remember, we learned all 6 of these different things up here. We're going to be tweaking one main value up here and see how it affects the other ones at the very end of our lesson today. But I want to make sure that we got the basics down from our last class, so you're going to answer a few questions here on the side about 2 different potential energy diagrams. So your question just asks you to tell me something about each one of these, and the main things are that potential energy diagram number 1 here is an endothermic process. You should be able to tell just by looking at this that this is the case. And the reason for that is because the heat of products is greater than our heat of reactants, meaning that by the end of the reaction, we have absorbed a certain amount of energy. Mathematically, you can prove this by calculating for the heat of reaction, which is equal to the heat of products minus the heat of reactants. For this graph, it's going to be 100 minus 50 to give you a positive 50 kilojoules. Whenever you have delta H ending with a positive value, you will know it is endothermic. This other graph, this is the one we focused on in detail, is the opposite because we end lower. We have an exothermic process, our heat of products is less than our heat of reactants, and delta H ultimately is a negative value. Whenever you have a negative delta H, you will know that it is exothermic, but if you're just looking at the graph, you should be able to tell just by looking at it. So in our first lesson of this unit, we started talking about how we can predict whether or not a reaction will go faster or slower if we change some of the things. We did a lab looking at temperature and surface area, which hopefully you have already finished that. And we're going to start to talk about these other ones today and focus most of our energy on the last one, which is catalysts. Okay, so we're going to go in order. When we're talking about nature of reactants, there's a few ways you can talk about this. You can talk about it in terms of what your substance actually is, whether it's reactive or not, whether or not it's an ionic bond or a covalent bond. But the biggest one that I would like you to focus on is the different phases of matter. So the question you're going to be asked is, which phase of matter do you think will lead to the most effective collisions and why? Not just general collisions, but effective collisions. Hopefully you said gas particles. Gas particles, although they are the most spread out, they are moving the fastest and they are moving the most, meaning that when they do collide, they're going to do so with a lot of energy. While solids and liquids are colliding a lot, they're not moving as fast, they don't have as much kinetic energy, and so that's not going to lead to as many effective collisions as if you had a gas of the same substance. That's not to say that solids and liquids can't react, but if they have the option to be a gas, that would mean that you would have the most effective collisions, and that would mean a faster reaction. Okay? The next one on the list is temperature. Not going to go into detail, but based on your lab, if you increase the temperature, this reaction will go blank because blank. We saw this with the Alka-Seltzer, that in the hot water, the particles were moving faster. This made the reaction happen extremely fast when compared to cold water, where your particles are moving slower. Similar to the last one, the faster your particles move, automatically the more effective collisions you're going to have, because when they bump into each other, not only are they bumping into each other more often, but they are doing so with more force. Concentration is a new one. Hopefully you remember that concentration is the amount of stuff you have per volume. We look at it mostly in terms of molarity, which is moles per liter, and so I want you to think about this for a second. If I take a substance, let's say I'm reacting my green and my red atoms here, and I add more of them, I increase the concentration, what impact do you think that will have on the rate of the reaction? Hopefully you said that when we have a higher concentration, as you can see here, we are going to have more molecules, therefore there will be more collisions. The rate of your reaction will be greater, meaning your reaction will be faster. I'm going to give you a real-world example here. If I am burning a flame, this is going to be a reaction between whatever is burning and the oxygen in the air. And so you can look at it kind of like this, where these blue dots represent the oxygen molecules that are part of this burning reaction. If I add more molecules, then that's going to make the reaction easier to happen because there's more stuff to collide. And so you're going to get a more vigorous flame if you have more oxygen. This is why when you're trying to start a fire, you fan the flame to try and give it some more oxygen. Okay? The next one's kind of similar, but it's very particular to one phase of matter, and that is going to be a change in pressure. Before we move on, what phase of matter do you think will be impacted by changes in pressure? If you remembered from Unit 4 when we talked about gas laws, we learned that if we change the pressure of a gas, you can also change other things about it, including volume, temperature, and things like that. And so I want you to think about that. If I increase the pressure on a gas, as you can see here, I'm putting more weight on the top of this piston, and I want you to look at what it's doing to the particles. What effect do you think this will have on the rate of the reaction? This is essentially the same as increasing the concentration, because on a gas, when you increase the pressure, you're pushing them closer together. Remember, smushing our invisible balloon. And when you do that, you push the particles closer together, pushing them closer together, more collisions, etc., etc. Okay? It's very important to know that this will only impact gases because liquids and solids are already too close enough to each other that a change in pressure is not going to change their volume. The next one we did in our lab, and it was surface area. So answer this question. Based on your lab, if you increase the surface area of the reactants, then the reaction will go blank because blank. Here is a little moving diagram of what's going on when we had the solid piece of Alka-Seltzer. The red represents the water here, and as you can see, they are only able to touch the ones here on the outside. The ones on the inside have to wait for the other ones to react. But if we break something into smaller pieces, what you do is you allow for more space for a reaction to occur. And so automatically, if you have more places for a reaction to occur, you're going to have more collisions, more effective collisions, okay? So those are going to be the main things that we can change that will make a reaction go faster or slower. And hopefully you notice that it is a pattern. If you increase any of these, you are going to have an increase in your rate of reaction, okay? It's one of the few things in chemistry where kind of everything has the same effect, Okay, the one to keep in mind is pressure is only going to impact gases, and similarly surface area really only impacts solids because you can't change the surface area of a liquid or a gas. Okay, so now the last one we're going to talk about is catalysts, and it's going to be the one that is the focus of our lab today. And so I'm going to show you a quick video about what catalysts are. Hopefully you remember hearing this word with Miss Caballo or Miss Yablon in living environment. But if not, let's watch this video and see if anything comes to mind.
In this video, you're going to learn what a catalyst is, how a catalyst works, and where catalysts are used in everyday life. Firstly, what is a catalyst? A catalyst is something which speeds up a chemical reaction, but at the end of the reaction has the same mass as it had at the beginning of the reaction. This means that it is not used up in the reaction. It must, however, take part in the reaction, or we might as well not have it there at all. So, how does a catalyst work? A catalyst works by providing an alternative pathway for the reaction to occur. This alternative pathway has a lower activation energy than the pathway without the catalyst. Here are the two pathways for a reaction. The blue pathway is the energy profile for the reaction without the catalyst, and the red pathway is the energy profile for the reaction with the catalyst. You can see here that with the catalyst the activation energy is lower. As a result of the activation energy being lower, there are more molecules with the required activation energy, and so more fruitful collisions occur per second, and hence the reaction is faster.
Alright, so hopefully you got the gist of catalyst and that you were able to summarize it on your Edpuzzle. But the main things about a catalyst are that it is a substance that will speed up a chemical reaction without reacting itself. Here's my face, sorry. And so it doesn't impact what your reactants are or what your products are, it just makes them react a little bit faster. Okay? The way that it does this is it does it by lowering the activation energy of a chemical reaction. So that's why we learned potential energy diagrams first before we start talking about these. But you can look at this little picture of the truck. Here the truck has to go all the way up the hill and over, but a catalyst is something that will provide it a shortcut to the end of the reaction. Okay, it doesn't react itself, it's just essentially a way to help it move faster. A place where you have heard about catalysts in the past are going to be biological catalysts or enzymes or hormones in living environment. Okay, so here is a quick illustration or animation about this. This is showing you a general reaction from where you start and you have to get up to that transition site. By the time you get up there, then your reaction can take place. Okay, but now by adding a catalyst, it's lowering that hill. Okay, and so it's going to make it so that it requires less energy to get over that hill. Okay, but if you notice, what's happening to delta H? Delta H is not being impacted at all. The reactants and the products are not being impacted. The only thing that's changing is the size of that hill, therefore the amount of energy needed to start or activate the reaction. Okay? So here is the potential energy diagram that we used when we first learned what they were, and we're going to go over the basics. And so here is our starting activation energy, just normal, okay? For us, it's going to be 100 minus 40, which is 60 kilojoules. If I add a catalyst, you're going to see this dashed line there, which is what the Regents would ask you to do. You simply lower this hill. And by lowering this hill, you are going to lower the activation energy. So I've labeled it here as catalyzed activation energy. It's basically what's happening. But notice delta H, HP, and HR have not changed. The only thing that changes is the beginning of that hill. So our initial activation energy was 80 kilojoules. With this catalyst, it's only going to require 40 kilojoules to start. Okay, so your to-do list today, hopefully you have finished all of this. You're going to be doing a lab. I'll see you there because I have more videos to show you. Please please reach out if you have any questions. Bye!